All right, so we're going to pick up where you guys left off in section 7.2 last time on operations of decimals, and we're going to pick up with the rounding. Oop, that was it. Okay, so we're going to take a look at what it means to round to the nearest blank, and this is left blank because it can be the nearest whatever, fill in the blank. So it can be the nearest hundredth, it could be the nearest hundred. It doesn't make any difference, but we have one of those descriptors of the place value that could fill in this blank. So we find the location that we need to round to, and then we look at the next place over. It doesn't actually say that. 0 to 4 means we round down, and 5 to 9 means we round up. So one of the things we're going to work on in this section is called rounding. We'll get to an example here in a second. But the other type of estimation that we're going to look at is called front-end estimation. Front-end estimation is really easy, but because it's one that's not always talked about, and it only comes up in certain resources, sometimes you haven't seen this one before. That doesn't mean you won't see it if you go out and teach this content because, as you know, curriculum changes. Front-end estimation uses the first value or the first couple of values, and it rounds off. So rounding off means that you're just turning everything after it into zeros, okay? You don't care if it go ups or down. It's just everything before the number stays the same, everything after the number becomes zeros. So it's a really easy process to do. And you probably use something like this all the time when you're actually trying to estimate something, is you say, oh, look, it's 312. Well, that's about 300, right? That kind of thing. That's really what that is when you're doing front-end estimation. So we're going to look at an example. Our example is going to be to round, and this one is to the specific value. And then we'll do our front-end estimation examples, example number 6. So the specified value is given in A, B, and C. The first one, A, says to the nearest hundred. What digit is the hundreds place in this problem? Yeah, the 2. So I'm going to rewrite our number each time. And the 2 is the number we're trying to round to. So we look at the next place over. That's the 0. The 0 tells us what we do. If it's 0 to 4, then we just turn everything into zeros and we call it good. If it's a number that's 5 to 9, then the number I highlighted in blue goes up 1. So the 2 will either stay as it is or it goes up 1. It doesn't ever go down. So this idea of it going down means that because the 0 is at the very end, everything turns into zeros at the very end, the value's smaller. But the 2 doesn't change when we're doing something where you're rounding down. So in this case, this number is a 0. So do we leave it as a 2 or do we move it to a 3? We leave it as a 2, right? It's in that 0 to 4 range. The 2 stays a 2, and everything else becomes zeros. So if you want, you can write 200. If you really want to write the other 3 as zeros, you can do that too. It doesn't hurt anything. Either way is fine. This would be our number. It'd be 200. The next one says the nearest hundredth. And I do these back to back because I want you to make sure you're paying very careful attention to the vocabulary that's being used. They don't mean the same thing, but they're easy to mistake for one another if you're moving too quickly. So what number is in the hundredths place? The 5. So this 5. What that means is the blue number that I highlighted, everything before it's not going to change. The blue number that I've highlighted is either going to stay the same or it's going to go up. And then the numbers after them are all turned into zeros. Okay? So we go to the number after to make the decision. It's a 1. What does the 1 tell us is going to happen to the 5? It's going to stay the same. So the number becomes 203, so 203 and 65 hundredths. If you want to write 650 thousandths like that, that's fine too. Either of those are perfectly acceptable. How about units? What does that mean? It is. It's the number before the decimal, or you might be thinking of it as the ones place, right? So in this problem, it's the number 3. Okay? So again, the 2 and the 0 before the 3 are for sure staying the same. The numbers after the 3 are for sure becoming zeros. The question is what happens to 3. So we look at the number after the 3. It's a 6. What does that tell us about 3? It goes up. So we've got the 2 and the 0 staying the same. The 3 rounds up to a 4. And again, if you want to write the zeros in afterwards, by all means you can, but you don't have to. 204 written as it is would be perfectly fine as well. I always feel like that by the time you guys get here, you're all really good with rounding. I mean, like pretty much. I mean, like you've seen it many times, right? The reason I mention this right now is because my third grader is working on rounding, not with decimals, but with whole number pieces. And she is struggling something serious. Like it is a really big struggle for her. So where do you encounter rounding for the first time? It's third grade. It's third grade. And I think she's finally got it down, but it has not been something that has come easily to her. So keep in mind, when you think things feel like they come easily, that doesn't mean they come easily the first time around in third grade or whatever grade that is, right? All right, front-end estimation is actually far easier, but there's a little bit less clarity to it. So you might notice that when we defined it back 2 slides before, front-end estimation says use the first value and then in parentheses or couple of values. There's usually not a real descriptive like this one was where it said round to the nearest and it gave you a place value, right? Front-end estimation doesn't usually do that. They sort of leave it up to you to decide maybe what makes sense in terms of the problem or maybe simply what you'd like to do. So I'm going to do this 2 different times, this problem, and show you what it looks like depending on what you decide to do. It will look similar, but there's 2 different ways. So we're going to first make the decision that we're going to round to the nearest, we're going to do front-end estimation to the tens place. Okay? This is our pick. We're going to do the tens place. We're going to do the units place in a moment just because I want you to see another option. But if we did this to the tens place, what that means we do is we take this number 89.47, we keep the tens place, that's the 8, and everything else zeroes out. It's just 80. And we take the second number, 32 and 16 hundredths, and we keep the threes place, or we keep the tens place, which is a 3, and everything else zeroes out. This is what front-end estimation does. It keeps the one digit and everything else zeroes out. Doesn't matter what came next. And we would subtract and we would get 80 minus 30, which is 50. I'm doing the track problem in the wrong order, I guess is what I'm doing. I'm sorry. I'm doing part B first. I was so excited to get to front-end estimation. Labeled it wrong. Let's do B. We'll go back and do rounding in a minute. I'm sorry. So we end up getting 50 for front-end estimation. Let's go back and then do the rounding with the tens place so that we can do it comparatively. So if we're doing rounding to the nearest tens place, it will not be quite the same. We use the tens place, right? I'll highlight them again in blue, the 8, the 3. But we make our decision based on what comes next. So this will be either an 8 or it'll go up to a 9. The 9 after it tells me what I do. Will the 8 stay 8 or will the 8 become a 9? It will become a 9. So I have 9, 0, and then we have 0, 0 if you want. You don't have to write it. 90 is fine. 90 is what's actually written in my notes. After that, I have the 3 and the 2. So I look at the 2, and the 2 tells me what's going to happen to the 3. Is it going to stay a 3 or become a 4? It's going to stay a 3. So 90 minus 30 is going to be 60, or 60.00 if you prefer. I'll just leave it 60 since the other one did. So I got different answers based on the strategy I chose and based on the fact that we did it to the tens place. So we're going to actually find the real answer, like the subtraction of what happens when we really check. It says how close are your answers. That means we have to actually do the problem. So this is 89 and 47 hundredths minus 32 and 16 hundredths. Okay, so if you've watched the video, you've worked through this. If not, just remember what you have known before or remind yourself of it. We start on the far right, just like we do with whole numbers. We do 7 minus 6 and we get a 1. And then we do 4 minus 1 and we get a 3. And inherent in what I already did on all 3 problems, the decimals have to be lined up properly to do this, right on top of each other. So the decimal comes down. 9 minus 2 is 7, and then 8 minus 3 is 5. And it's an interesting thing. I don't know why I was going to put dollars in there, probably because it feels like a dollar amount. It's an interesting thing because the 57 is in between our 2 estimates, right? That's typical. I mean, like we would expect that to be the case. We should be close. And in fact, we're on either side. And this particular one, the one that's a better estimate, is rounding, and that's usually the case. Rounding is usually a better estimate. This was to the nearest tens. We chose that. But we could have chosen the ones place if we wanted, or something else. If you don't do just a few, you're kind of missing the point, right? Because I only have 4 numbers, right? I mean, like if I use 3 of them, what was the point in not just keeping the 4th one, you know? Let's do it with 2 numbers just to see what it looks like and do it to the units place. So units place makes a lot of sense with these particular numbers as well because they do feel like dollar amount numbers. And usually we don't care that much about our coins. It's just kind of how we are, right? But we usually care that somebody gave us back the right dollar amount when we're getting change somewhere, agreed? Usually that's a value to us. So sometimes we care about the coins too. It depends on who we are. So if you're my daughter who likes coins, and she just likes the shiny coins, she cares. But anyway, so let's do it. I'll just do this in the same order so that it matches up from what I did last time, since my B and my A are backwards. And we'll do this to the units place. So if I do this to the unit place, I keep the first 2 values. For front-end estimation, I just keep what's there. It's 89. And I zero everything else out. And then I just keep what's there for the next one. That's a 32. And then I subtract. So 9 minus 2 is 7. And 8 minus 3 is 5. And that's really close. I mean, it's really, really close. And interestingly enough, on this one, if I do this with rounding, this is why I didn't do it to begin with as the units place. If I do this with rounding, it hardly changes. So let me erase this part where I highlighted. So now we're looking at the units place, and we're looking at the value right afterwards. So I have 89, and then I've got a 4. So what does the 4 tell me about the 9?
It stays the same.
It stays the same. So the 89 will stay 89. And then over here, the 2's, the 2, and then the 1 right afterwards. The 1 tells me what happens to the 2. It stays the same. So on this one, rounding and front-end estimation end up being exactly the same. So they don't have to be exactly the same, but here they are. And we get 57 in both cases, which is a really good estimate when 57, and 30 and 3100ths is actually our answer for doing it all out. Okay, it's good? Okay, our next example is a very interesting one, and you're going to want a calculator. So grab a calculator out. If you don't have one and you want to use your phone for this one, you're going to need it. So just grab something, otherwise it's not going to make any sense what we're doing. All right, so this is one of those type C questions where it's an application, sort of a nuance to something. So a student tries to calculate 0.999, so 999 thousandths, to the power of 10,000 on a calculator, and finds that the answer is 4.5173346 times 10 to the negative 5th. Okay, that's almost 0, right, to the negative 5th. We did scientific notation in 7.2 before this lesson, okay? This is a very, very small number. It's almost 0. The student wonders how it could be that a number like 999 thousandths, which is so close to the number 1, right? So close that the gas station does it and we just ignore that last 9. Y'all know what I'm talking about, right? So close to the number 1, when raised to a power, could end up in an answer that's so close to the number 0. How do you respond? So we're going to play with our calculators with this idea for a moment and see what's happening here, because it is interesting and it does feel a little bit odd. I mean, how do you take the number practically 1, raise it to a power, and get almost 0? Most of the time you take the number 1 to something and you get almost 1, right? 1 squared is 1. 1 to the third is 1. Like, what's the deal? What's happening here? So here's what we're going to do. We're going to consider changing the exponent and letting it get slightly bigger each time, but in a really specific way that's easy for us to work with. So we're going to consider the 0.999 and just squaring it. So we're just going to square it. So grab your calculator, point the 9's in, and raise it to the power of 2. And what do you get?
0.9980001.
Okay, Bigger or smaller than you were before?
Smaller.
Smaller, but not very much smaller, right? I mean, it's still 99 cents. If we had to round it off, we would say 99 cents. The other one, we guess we would say probably $1. But yeah, I mean, it's still very, very close. And then square again. So the way that you do that is you take the previous number, in this case it's 0.998001, and you square that. So in your calculator, you can probably just hit the squaring button again, and it'll automatically square the previous answer that's in your calculator. So that's why it's convenient to do this powers of 2 repeatedly. This is 0.996. And I'm going to use 6 decimals on all of them since we started out with something with 6 decimals. Works out nicely. It's 0.006. Okay, so we've talked about properties of exponents back in chapter 6. May not have been your favorite topic. That's okay, but we talked about it. When I raise it to a power of 2 and I raise it to a power again of 2, that's the same thing as 2 times 2, which is 4. So the result of what we just found out really is the same thing as finding 0.999 to the 4th. That's what we just did. So we're going to do this, and, good grief. Again. So we're going to take the value that we just got on the last line, which is 0.996006. If you have the ability to keep more of the decimals in your calculator to do it, it'll keep the accuracy a bit longer. So if I just hit squared for me, it keeps all my decimals and does it. And I get 992028. Okay. It is going down still, right? The number is slightly smaller. How big is the power really now? I've squared it 3 times. It's 8. 2 times 2 times 2. This is a power of 8. Now we're still nowhere near a power of 10,000. But you should feel like, but it is getting smaller. But still, like, it's not getting smaller fast. It's doing it really slowly. So we're going to do it again. So now we have 0.992028, again, squared. And all of a sudden we lost a penny. 0.984119. And if you were my daughter, you'd be very sad to lose that penny. What power are we really at when we've done this 4 times? 16. And if you aren't sure how Lauren's or how Addie's getting that, what's happening is we're multiplying by 2 on the powers each time because we're raising it to another power of 2, and a power raised to a power's multiplication. So that's what's happening to get that extra value. So we're going to do this again. There is a stopping spot. We're going to do a few more iterations, I promise. We will stop eventually. 98419 squared. We lose a few more pennies. 968491. What power have we arrived at? 32, yeah. Let's go again. 0.968. Would it help you to know how many times we're going to go, just to give you an insight? Okay, let me write this one down and I'll count it. This is 937975. We're going to do it 4 more times. Okay? Y'all can do it. I have faith in you. No problem. You might have to think through how big the numbers get on the exponents here, though. After 32, what's next? 64. Yeah. Okay. And you said you're going to have to write smaller. Well, I'm going to have to write smaller too, but I can also shrink my screen, which will help. All right. 9379. Ugh, it's not working for me. Let's go smaller on my pen stroke. 937975. That's not too bad. Okay. And we've crossed the threshold, and we're no longer in the 90s, we're in the 80s. 879,797. And this is 0.999 to what power? Where are we now? 128. You guys are doing good. Yep, we're at 128. So at this point, we've lost 12 cents, right? We've lost about 12 cents on this this dollar, if you will, if we're thinking in terms of dollars. So now we have our 879797 and squaring that. And this one's an interesting one. How much do we lose this time? Almost 10 cents, right? I mean, like it's estimated of 10 cents. 404.3. Just in that single move, we've actually seen a lot of change. And remember, the reason we're seeing a lot of change is because we're not, I mean, I know we're squaring things each time, and it might not feel like that's a lot, but the exponent that's really happening is changing substantially, right? At first, the exponent went from 8 to 16. That's not a very big jump. But to have the exponent go from 128 to the one we have now, which is what? 256. That's a big jump. Very big jump. So we're going to do 2 more. So the next one is maybe it's 2 more, 77,404.3 squared. I'm trying to get to an exponent that's almost 1,000. That's what I'm trying to do, just so you know, is that why I'm doing the numbers I'm doing. So 0.599142. Do you know where my exponent is now? It is 512. So one more iteration will get me to the power of 1,000. So 0.599142, which is, I mean, we're almost half of where we started. We started with a number that's almost 1, and we're at a number that's 0.6. We're at almost half. And where does this leave me? Mm-hmm. And what power am I at now? 1,024. So what's going on? Well, whenever you multiply, and this will come up in your homework in a different question used in a different context, but whenever you multiply by a positive value or number, if you prefer, less than 1, which is what we are. We're multiplying by 0.999. That is a positive value less than 1. So anytime you do that, the product is smaller. So the product becomes smaller. And here, we do this 10,000 times. We did it the equivalent of about 1,000 times here in a shortcut sort of way of doing it. But you can see how drastically that's dropping even as we went, right, eventually. And you can see how it's plummeting down. It never goes below 0, though, right, because below 0 would be negative. This doesn't create a negative number, but it does create a number that's smaller and getting infinitely smaller as we go. Interesting, yeah? It is interesting. It's an unexpected result.